Okay, at this point in the module, you should have a calibrated measurement of the brightness of Jupiter at radio wavelengths. You might have two of them. If your team put in two observations of Jupiter, you have two measurements, and you can check them against each other. They should be about the same. The question is, what's causing that radio emission? Is it thermal, or is it something else? Let's investigate the thermal hypothesis first. Anything with temperature emits radiation, emits light. Sometimes it's light you can see, and often it's light you can't see. So you get a spectrum of light. And that's what we see in this plot here. We see different thermal curves, sometimes called blackbody curves. On the x-axis, we have frequency. And in this range, you can see the frequencies of visible light. You go to higher frequency waves, and that's ultraviolet light, and lower frequency waves, and that's infrared light. And if you keep going off the left-hand side of this plot, you're down into the radio regime. And you have different curves for different temperatures. Take yourself, for example. You or anything about you is about 300 Kelvin. That's about room temperature. So this curve represents anything at room temperature, including yourself. And notice it does not intersect the visible band. You're not emitting visible light. You're not glowing. But you are emitting in the infrared, and we detect that as heat. And if you follow this curve all the way down off the left-hand side of the plot, you're also emitting a little bit in radio. So we can use these curves to figure out Jupiter's temperature. We can use our radio telescope as a giant thermometer to measure the temperature of Jupiter all the way from here, if it's a thermal emitter. Now, down in the radio regime, far from the peak, we call that the Rayleigh-Jeans limit. And the equation simplifies a lot down here. The amount of flux that you receive depends on a number of things. First of all, the temperature. The hotter the object, the more radio waves it emits. It also depends on the surface area of the object. The more surface area through which it can emit, the more radio waves you receive. And for planets, they're spheres, so the surface area is proportional to the radius squared. So the temperature that we calculate will depend upon the radius squared. It's also a function of how far away the planet is. The farther away something is, the fainter it will be. And that's a 1 over distance squared effect. Lastly, it depends upon the frequency that we're looking at. As you can see from these curves, the higher the frequency, more radio waves are emitted for a thermal emitter. Now there's a derivation for this equation and the Rayleigh-Jeans limit. You can see the derivation here. And here it is solved for temperature. So we're going to go through this here, this calculation. S is the flux, the brightness. S sub nu is the brightness at a particular frequency. Nu means frequency, the frequency of the light. So S sub nu is your Jansky measurement, but you have to convert it to MKS. And so 1 Jansky is 10 to the minus 26 watts per meter squared per hertz. So you'll take your number of Janskys, multiply it by that, that goes here. Then you have a bunch of constants. Here's Boltzmann's constant. This is the speed of light. Again, nu is the frequency at which you observed. We observed at 1395 megahertz. That's 1.395 times 10 to the 9 hertz. Here's the distance squared. Here's the radius squared. So we know all these things. We've measured the brightness. We know everything else except the distance. That varies with time because both Earth and Jupiter are orbiting the sun. So our distance apart varies with time, and we can get that from Stellarium. Okay, so let's go to our temperature calculation spreadsheet. Here I have the date and time of my observation from above on the spreadsheet. Here I have my measurement of the brightness of Jupiter in Janskys. Now, for this video, I just put in the number 3. You'll make your own measurement. It's something like that. It's only a few Janskys. It's pretty faint. And using this information, we're going to calculate the temperature. Everything we need is here. We have the flux. We have all the constants that we were talking about. The only thing we need is the distance to Jupiter at the time of the observation in kilometers. So for that, we go to Stellarium. First, you want to go to the location window, use custom time zone and change it to UTC to match the date and time that you have. Then go to the date and time window. This particular observation was taken January 22nd at 22 hours and 20 minutes. Then I want to find Jupiter. Okay. And at that time, the distance to Jupiter is right here. We have two things. We have distance from the sun. We don't want that. And we have the distance from us. And what we want is the distance in kilometers. That's the number here in the parentheses. 721 million kilometers. That M means million. So times 10 to the 6. So 721 e to the 6. Change that to 7.21 times 10 to the 8. Okay, now we have everything we need to calculate the temperature. For that, we're going to use this equation, but I'm going to do it in the spreadsheet. That temperature is equal to the brightness, the flux in Janskys. We multiply that by the conversion constant right here. Divide by 2, divide by Boltzmann's constant here. And we multiply by the quantity. So parenthesis c, the speed of light, divided by our frequency of observation, on parenthesis squared. Let's check our formula. That's this. And then we multiply by the distance here, squared, divided by pi, divided by the radius of Jupiter right here, squared. So everything you need is here, enter, and I got something 1.7 times 10 to the 3. That's about 1,700. Now you'll get your own measurement. The thing you need to ask yourself, is this a reasonable temperature for Jupiter? Earth's temperature in Kelvin is 288. And Jupiter's much farther away. It's about 5 times farther from the sun, the source of heat in the solar system, than the Earth. So you should expect Jupiter to be colder than the Earth. And in my calculation here, I got it as hotter. You'll have to see what you get for your own calculation. But if it's hotter, that means the radio waves that we're detecting probably are not thermal emission. It's probably something else. So what else could it be? Well, this is your first introduction to synchrotron radiation. In this course, you're going to learn about different types of radiation, different ways to emit light, whether it's visible light or radio light. Synchrotron is a very important mechanism. We have it whenever we have energized electrons in magnetic fields. Those electrons will spiral around the field lines, and as they spiral, they emit a synchrotron spectrum of radiation. So here you see electrons spiraling around magnetic field lines. Here, the purple curve is a typical thermal spectrum, again, frequency on the x-axis, but synchrotron is very different. It's more of a straight line in this plot and tipped the other way. Down here in the radio, thermal is tipped this way, synchrotrons tip this way, and there are many instances where the synchrotron emission can outshine the thermal emission. Jupiter does have temperature, it does have thermal emission, but Jupiter also has very powerful magnetic fields. And if charged particles get trapped in those field lines, you can get a lot of synchrotron radiation outshining the thermal emission. Probably the best example of synchrotron emission in our solar system is from the sun. The most powerful magnetic fields in the solar system are on the sun, and they're tied to the sunspots. So here's a diagram of the sun. Sunspots occur in pairs, and they're caused by when the magnetic field exits the sun and re-enters. And they give you dark spots at visible wavelengths. But this picture was taken by the Very Large Array in New Mexico, an interferometer at radio wavelengths. In fact, the same frequency that you're observing with the Green Bank 20 meter. And you can see in the radio, the sunspots are not the dark spots, they're the bright spots because of that synchrotron emission. Those are the spots where you have very strong magnetic fields. It's a hot gas, so you have charges, electrons roaming around free, and they get stuck in the magnetic field lines. They spiral around them, they emit synchrotron radiation. This much fainter blue haze that you see in the background is thermal emission from the surface at radio wavelengths, but the sunspots are giving synchrotron. Now, in the case of Jupiter, I already said it has a very strong magnetic field. It's not as strong as the sun, but it's much stronger than any planet in the solar system. We discovered it back before the Voyager missions. The Pioneer mission, Pioneer 10, as it passed behind Jupiter, it passed through its magnetic field. We never expected it, but its magnetic field is pushed by the solar wind. There's charges flowing off the sun, and it pushes the magnetic field, stretching it out, and we passed through it, even though we were beyond Saturn at that point. Here's a diagram closer in of Jupiter's magnetic field. Again, charged particles come from the sun. Some of those get trapped in the magnetic field, spiral around the field lines, making radio emission. There's a second source of radio emission as well, and that is the Io plasma torus. Io, Jupiter's innermost moon, orbits within the magnetic field, and it's a volcanic moon. And from its volcanoes, it's spewing out charges. It then gets stuck in the magnetic field, again, making synchrotron radiation. In fact, I'm going to show you a video. This is a movie made by a radio interferometer in Australia. The sphere at the center is just for reference. That's the size of Jupiter. But the blue haze is the synchrotron emission coming from about it. The little bit on top and a little bit underneath are pockets in Jupiter's magnetic field where charge gets trapped, kind of like the Van Allen belts here on Earth. And this belt around the middle is the Io plasma torus. This is charged particles coming from the volcanic activity on Io entering Jupiter's magnetic field. And that is a radiation hazard zone. It's one of the most dangerous places for life in the solar system. Once we eventually get out there, it'll be something to avoid. All right.